Let's reconsider the situation where two bolted members are in tension as shown below, but this time focus on the bolt. As the top plate moves right and the bottom plate moves left, the bolt will experience shearing at the interface of the two plates, which is a cross-cutting action that's imparted onto the bolt. As a result of the cross-cutting action, the bolt experiences a shearing stress, tau sub ing. Shearing stress, like all other types of stress, is the applied force over the area the force is acting on, shown in the equation below. The area this force acts over is the cross-sectional area of the bolt, which is shown by the red circle in the schematic below. In this situation, the bolt is said to be experiencing single shear, as the shearing is only occurring in one location. Let's apply this to a bolt experiencing double shear, where three members are bolted together. Given the diameter of the bolt is equal to 12 millimeters and the force acting on the members is 1 kilonewton, find the shearing stress in the bolt. Now, there are a couple ways we can go about this. One way is to imagine the top plate is moving to the right and the other two plates are being held stationary. In this situation, we're interested in the first shearing plane, shown by the red dashed line. Since the top plate is the only one moving, the force exerted on the shearing plane will be F per 2. The area the shearing is occurring at will be the cross-sectional area of the bolt, which is equal to pi d squared per 4. Recalling that shearing stress is force per area, we have the applied force 1,000 newtons per 2 divided by the cross-sectional area of the bolt, pi times 0.012 squared meters per 4. Rearranging, we get 4 times 500 newtons divided by pi times 1.44 e to the minus 4 meters squared, which is equal to 2,000 newtons per 4.52 e to the minus 4 meters squared, ultimately giving us a shearing stress of 4.42 megapascal. We can also use the same process with the bottom plate. Focusing on the second shearing plane, we recognize the bottom plate is applying the force, so the force in our equation is F per 2, and the shearing stress is occurring over the cross-sectional area of the bolt. The shearing stress is then equal to the applied force per the area it's acting on, which is equal to 4 times 500 newtons divided by pi times 1.44 e to the minus 4 meters squared, which is equal to 2,000 newtons divided by 4.52 e to the minus 4 squared, which gives us a shearing stress of 4.42 megapascal. We can also imagine the middle plate moving while the top and bottom plates remain stationary. In this case, the applied force F is causing shearing to occur at both shearing planes. Since the force is acting on two shearing planes, we will multiply the cross-sectional area of the bolt by 2 in the shearing stress equation. We can calculate the shearing stress as 4 times 1,000 newtons divided by 2 pi times 0.012 meters squared, which is equal to 4,000 newtons per 9.05 e to the minus 4 meters squared, which gives us a value of 4.42 megapascal for our shearing stress. We can see that each of the three approaches for this problem gives the same value for the shearing stress in the bolt. Because stress does not have commutative properties, both interfaces see a shearing stress of 4.42 megapascal due to each interface experiencing a force of F per 2. It might seem counterintuitive that the answer we got from the previous approach is for only one of the shearing planes. However, if we imagine cutting the bolt in half, the force is split between the two shearing planes. The bolt is in equilibrium, so the force F per 2 pulling to the right is counteracted by F pulling to the left.